Hello friends, today we will start with the next strengthening mechanism, okay, and that strengthening mechanism is particle or precipitation hardening. So basically we have already seen that we can have small precipitates within the grain, okay, and these precipitates can act as a barrier to the dislocation movement, and that is how you can give strengthening to the material. Okay, so one of the very important mechanism for giving strength to aluminum alloys, okay, and some of the super alloys which are used in high temperature applications, okay, for example turbine blades and so on. These precipitates are very important, okay, to give strength to the material. Okay, so if we want to see the interaction between precipitates and dislocation, okay, it is a very important hardening mechanism, more effective than solute atoms. We have already, I have already told you that solute solution hardening, okay, or hardening because of the solute atoms is not a very strong obstacle, it is a weak obstacle, okay, because there is a very small strain field associated with solute atoms, okay, that interact with the strain field of dislocations, and that is how you get the hardening. Okay, so it is not a very effective one, but if you can get precipitate in the material, okay, from the same solute atoms, okay, if you can have precipitates, then the precipitates are very potent hardening mechanism, and it is used in large number of alloy systems to impart strength, as I just told you. Okay. So, the strengthening, if you see, okay, strengthening depends on particle size, particle volume fraction, particle shape, okay. So, size, of course, if it is small or big and so on. Particle volume fraction means how many or what is the total fraction of those precipitates with respect to the fraction of the parent phase, okay. So, what is the fraction of that? So, more the fraction, it is better. Particle shape, if it is spherical, if it is a kind of a plate kind of shape and so on. This is one of the most important, nature of the interface between the particle and the matrix, that what kind of interface is there. Okay, I have touched upon this particular aspect earlier also, that the interface can be coherent. Okay. In that case you will see that the atomic arrangement is continuous throughout, from precipitate to the matrix, the arrangement of atom is continuous, okay, and you will not see any change in the arrangement. If it is incoherent, then it will be totally different, the crystal structure, the atomic arrangement will be totally different between the two, okay. And what is the structure of particle, crystal structure? So, if we want to see the nature of the particle, as I just discussed, there can be different ways in which particle can be can have interface with the matrix. Okay. So, for example, the first one, the completely coherent precipitate, you see this the dark phase here is shown as a particle. So, it may be of some other solute atoms are there, maybe some different crystal structure is there. Okay. But the important thing here is that if you see consider this the grid as the arrangement of atoms, so this can be considered as crystallographic planes also. Okay. So, if you see the plane which is going in the matrix like this, it is continuous in the precipitate also. Okay. So, there is no break in the arrangement, and it look like a continuous arrangement. Only difference will be that there is a difference in the chemistry within the precipitate. So, you may have more solute atom here, less solute atom in the matrix. Okay. So, only difference will be the that it has different chemistry, otherwise the lattice parameter and the structure is more or less same. I can have coherency, but there may be slight difference between the way the atoms are arranged in the precipitate and the matrix, though the arrangement of the atoms in the precipitate and the matrix is same, but the lattice parameter is different. Okay. So, arrangement is same, they are arranged, let us say if it is FCC, so both it is FCC, but the lattice parameter can be slightly different. So, my precipitate can still maintain the coherency across the interface, okay, but with some kind of strain. Okay, so you can see that there is a strain in the matrix around the precipitate. So you can see in the precipitate we have made the grid finer, the grid in the matrix is little bit coarse. So lattice parameter of matrix is more, lattice parameter of precipitate is less. So you still can maintain the coherency, but you have to have some kind of strain. Okay, I have to stretch the bonds and so on, okay, to maintain the coherency. So depending upon whether the precipitate is soft or the matrix is soft, the strain will be accommodated in that particular phase. So in this case we are assuming that the matrix is soft in comparison to the precipitate. So you can see the whole strain is accommodated by the matrix. Now sometime it may happen that my this material is highly strained, so it does not want to be in that strained condition. So we can convert this kind of situation into a semi coherent interface, where now you have a dislocation which is accommodating the strain. So if you have too much strain, what you can do, you can insert an extra half plane, okay, and thereby you can relieve the strain in the other atomic planes. For example, you can see here that in this there is a continuous arrangement here, okay, you have continuous arrangement here, okay, but this atomic plane is not having any corresponding plane in the matrix. So this is kind of a dislocation in the matrix which is now able to accommodate all the strain in the you can say y direction. For example, if you take this as x direction, so in y direction the arrangement is coherent, okay, but in this interface it is semi coherent, okay, some dislocations are there. And in case of incoherent, you can see that the grids are totally different. What we have, the grid in the precipitate is totally different than the matrix. And again you can see that it is trying to have a spherical shape. So we started with a spherical shape, and in incoherent phase also we are trying to have a spherical shape. The reason for that is that I want to reduce the interfacial area, okay, or I want to minimize the total interfacial area, okay, and for the given volume we know that sphere has the minimum surface. So because incoherent, when you have incoherent interfaces, the energy of the interface will be very high, so it will be high energy interface. So to minimize the interfacial area, my precipitate would like to have a spherical shape. This is already we have seen that you can have different stages of precipitation, and depending upon that you will have different hardness, okay. So coherent precipitate, small particle, small interparticle spacing, okay. So you have numerous small GP zone, and the distance between those GP zone is also very small. Then you can have semi coherent precipitate in the stage second, okay. So this is my stage 1, this is my stage 2nd, and third is incoherent precipitate, large particle, large interparticle spacing. So in this, when it started coming down, that is my stage 3, okay. So you can have this type of stages. Already we have discussed about this when we were discussing about precipitation. So now we will also discuss in terms of that how dislocations are going to interact with the these precipitates. At that time we did not talk about this, okay. So how now the strengthening will come in this type of precipitation, okay. So you first step is after quenching, okay. When you are doing a quenching, only you have solute solution hardening. That means all the solute is in supersaturated condition, of course, it does not want to remain in the matrix, but because we have quenched, it is in that condition, okay. So in the stage 1, just after quenching, whatever strength you will get is only through solute solution strengthening, okay, because all the solute is in the solution, okay. Then comes the next part, that you now require extra stress required to force dislocation through a coherent zone. So you have those GP zone which has coherent interfaces. Now my dislocation has to go Suppose you are talking about aluminum and you are talking about this copper GP zones. Okay. So, when my dislocation is moving, okay, so it has aluminum atoms. So, aluminum have its own bond energy. So, when dislocation is moving, it is breaking bonds and forming new bonds. In the copper, where the copper rich GP zones are there, the bond energy will be different. So, when it is going through this because of this different atmosphere, you will require an extra stress to move the dislocation, okay, and that will be seen in the initial part of the hardening and during aging process. Okay. The third stage is when dislocation is forced through highly strained matrix because of misfit. Okay. So, misfit perpendicular to theta double prime plates. Okay. So, that is there are different type of precipitates, as I told you, which form during the precipitation sequence. Okay. So, these have semi coherent interfaces. Okay. So, my dislocation has to move through this kind of interfaces. Okay. So, you need now extra stress to move the dislocation, and that is what you can see in the hardening of this particular aging precipitation sequence. Then the precipitate size increases, spacing between precipitate increases, okay, and now dislocation are able to bow between the precipitate. Okay. So, that is the stage when it started coming down. My size has increased and my interparticle distance has also increased. Okay. So, now dislocation can move by bowing between the precipitate. We will see all this mechanism in the later slides. So, these are the different interactions between the dislocation and the precipitate during the aging process. Okay. So, now there are two ways in which dislocation and particle can interact. One is dislocation cut through precipitates. Okay. So, this is how the shearing process is there. So, cut through, or you can say shear through. Okay. So, either it can be shearing of the precipitate, or you can say it is cutting through the precipitate. Okay. So, you can see that dislocations are precipitates are shown here, spherical precipitate. So, they have shown a cut section and the dislocation is moving. Okay. So, they are showing successive position of the dislocation line, okay, and force is applied perpendicular to the dislocation line. Okay, and it is a spherical shape. So, when the dislocation is moving through the matrix and through this precipitate, spherical precipitate, then it is cutting it, and when as we know that when the dislocation move, my plane slide by one atomic distance, so equal to one Berger vector. So, similarly the precipitate will also displace by that amount of distance. Okay. So, that is what you can see here, that my precipitate is displaced now, okay, by some amount equal to the Berger's vector. Okay. So, this is one mechanism with cutting through the precipitate. So, it is like a knife cutting through something, or it can bow around the precipitate. Okay. So, another mechanism is that this is a dislocation. Okay. So, it is bowing around the dislocation. Okay. So, it is like again kind of a arrow and bow kind of thing, that you are stretching the bow. Okay. So, it is like, that is why it is called bowing around the precipitate. Okay. So, these are the two ways, okay, which will be applicable in which condition, that we will see now. So, shearing or bowing depends on the properties and distribution of particles. Okay. So, for example, you can see here that the underaged or the coherent particles, okay, you have shearing type of processes. So, particle gets sheared because it is already coherent. So, dislocation can move in the same atomic plane without any problem. So, when it is a coherent precipitate, you have shearing. Okay. So, this is cutting or shearing, in this it is shear, and for incoherent overaged particles, okay, you have looping or bowing in this direction. Okay. So, bowing in this direction and cutting in this direction. So, weak obstacles are dislocation is able to cut, strong obstacle it likes to bow around it. Okay. So, if it is weak I can easily cut through it, if it is strong or if it is hard then the dislocation like to bow around it. Okay. So, these are the two ways, and I can also give you a interparticle spacing of any precipitates. Okay. If I know the volume fraction of the precipitates, okay, and what is their radius, if it is a spherical precipitate. Okay. So, this is not properties, radius of the spherical precipitates and this fraction. So, if I know fraction and the radius I can give you that what will be the interparticle spacing between the two. Okay. So, as shown here as L, the particle spacing between the two precipitates. I will keep on using sometime particle precipitates, these are two same things. Okay. So, you should not get confused in this. So, coherent precipitate, so as I told you that there is can be shearing or can be bowing. Okay. Shearing usually takes place when your precipitate is weak. Okay. So, coherent precipitate, because there is a coherency, the interface is very low energy. Okay. So, the dislocation precipitate shear through the precipitate. So, a small soft coherent particle with a small interparticle spacing, in this case the bowing stresses will be very high. Okay. So, because of coherency it is easy to shear through it. Okay. So, as you can see there is one nice micrograph is shown here. So, the dislocation has moved through the particle. So, it is now sheared by one Berger's vector. So, after the shearing a new interface is created between particle and matrix which give rise to its strengthening due to increase in interfacial area. So, it is like this, if one dislocation moves it is easy for first dislocation to move. Okay. But what will happen, because it has created these two new interfaces. So, earlier only the interface was due to the spherical nature of the particle, but because of the cutting now the total interfacial area is like this and there is creation of two new interfaces here. So, now when the next dislocation comes, for that it will be difficult for the next dislocation to move through the same plane, okay, from which has moved. Okay. So, now the strengthening is there because of increase in the interfacial area. Okay. For large incoherent precipitate, so the earlier one was for small coherent precipitate. For large incoherent precipitate, R01 looping will be there. Okay. It was proposed by the scientist and on his name it is called R01 bowing or R01 looping. Okay. So, it is bowing instead of shearing now. Okay. So, basically this is again a micrograph showing the bowing process. Okay. So, you can see a dislocation is bowing between these two particles here. Okay. So, the total mechanism, if you see, this is my dislocation line, these are the precipitates. Okay. So, when in the next stage, so this is my first stage, next stage they are bowing between the precipitate. Okay. If I keep on applying the shear stress, okay, what will happen, it will bow more. Okay. So, you can see it is how it is bowing. Okay. And what will happen, these two will have two different Berger vectors, just opposite Berger vector. So, later on it will annihilate each other. So, what will happen, you will leave a loop around the precipitate and the dislocation will go through. Okay. So, these are the four stages in which the dislocation interacts with the precipitate. So, these are large precipitate with more spacing. Okay. And these are the four steps of how the bowing takes place between the precipitates. Okay. Very similar to Frank Reed source, if you remember. Okay. So, there we said that you have now one additional dislocation loop in each precipitate. Okay. Now, how the strengthening comes through this process. So, when the one dislocation moves, okay, it has left these loop around the precipitate. Okay. So, now the earlier the interparticle spacing, if you, so this is the distance between the precipitate. So, now when the loop is left behind, okay, so now the effective distance between the particle has become L prime, and L prime is less than L. So, when one dislocation goes through this and leaves the loop, now my distance between the particle has decreased. So, for the next loop, when the next dislocation when it comes, it sees a smaller interparticle distance. Okay, so it will become difficult for it to loop through. You can see that if I bring the anchor point very close, I will have to apply more stress for the bow. Okay, so if I have a longer string, I can easily stretch a string. If I bring anchor point very close, it will be very difficult for me for the same string, very difficult for me to displace it by the same amount. Okay. So, that is what you get the strengthening as the dislocations are moving through the precipitates. Now, what is the effect of volume fraction on bowing stress? Okay. So, these are the two curves. So, this is my stress required for bowing, and this is my particle radius r. Okay. So, there are two different volume fractions of precipitates. Okay. How I can change the volume fraction? By taking an alloy of higher solute content. So, if I want to have more volume fraction, okay, I will increase the solute content in the my alloy. So, for example, this is for let us say, just for argument sake, it is for 2% copper, this should be for aluminum 4% copper. So, I have more copper, so more precipitates will form. So, I will increase the fraction of the precipitate. Okay. So, this is how the precipitate fraction will increase, and if I have increased fraction for the same radius, for example, if I want to compare between the two fractions. Okay. So, for this radius r1 here, this will be the stress required for bowing. For the same radius, if with higher fraction, will be the stress required for bowing. Okay. What will happen with this when the radius is same and the fraction is increasing? Suppose I take a volume of material like this. Okay, radius is same, but fraction is F1, for example, in first case. So, let us say these are the precipitate arrangement. Okay. So, this is my distance between the particle. Okay. So, for the same volume, if I take for F2. Okay, now radius is same, but fraction is more. So, I have to have precipitate very close to each other. Okay. And now the interparticle distance has come down, let us say call it as L2. Okay. So, L2 is less than L1. So, my bowing stress will be more. Okay. So, and that is why you will require higher shear stress for bowing. Now, just a comparison between cutting or bowing, okay, that the particle size, for small particle size, shearing will be the dominant mechanism. For larger particles, bowing will be the dominant mechanism. You can understand that a small particle I can easily shear. If it is a large particle, shearing will be difficult. So, instead my dislocation would like to bow around it. Particle spacing, if particles are close to each other, interparticle distance is less, okay, then shearing will be the dominant one, and if the particles are far apart, okay, or interparticle distance is more, then the bowing will be the preferred mechanism. Particle nature, for coherent particles, shearing will take place. For incoherent particles, bowing will be the preferred mechanism of the deformation. Okay. So, with this I would like to thank you. This is a very important, one of the important strengthening mechanism through precipitates. Okay. And depending upon what type of precipitates are there, you can have different mechanisms. Okay. And you can also understand that as the dislocations are moving through the precipitates, okay, slowly the material will start getting strengthened. Okay. So, after movement of one dislocation, when the next dislocation comes, it will be even difficult for the next dislocation to move through the same number of precipitates. Okay. So, thank you very much.